let's go for it. Okay, so hopefully you can all see my PowerPoint presentation. Hello, my name's Dr. Andrew Blyth, and I work for Merrimetso. Spent the last 20 or so years basically working in the area of cybersecurity, forensics, breaking into stuff, and then in the forensics point of view, figuring out how stuff got broken into. My last job, University of South Wales, we were the first people to do forensics on the iPhone, Xbox, which involved a bunch of students spending a week eating pizza and playing Guitar Hero and Call of Duty, which they thought was great, to put data on the device. So you name it, we've pretty much played with it, hacked it, done forensics on it. So what I'm going to do today is talk about some of the changing world of forensics and forensics in the IoT space. And I'll talk about the challenges and things. In order to understand the problems, we need to understand the traditional view of forensics. So having done forensics, I'll talk about what forensics is and how we do it. I'll then talk about what I mean by the Internet of Things, because there's this annoying word at the end called thing, which kind of means everything. I'll talk about some of the challenges, and I'll talk about the process model and things like that. Hopefully we'll get this done in 45 minutes, and we can have plenty of time for questions, discussions, debate. So it's taken off, right? IoT. Actually, IoT's been with us a long time. It's been with us since the beginning of computing. If you go back to a lot of the industrial process control systems like power grids, water sewerage, and things like that. Nothing new. It's just that these systems that were never designed with cybersecurity in mind have suddenly become critical to our lives, such as taking the power down in Ukraine. We've also got petrol pumps attacks and water attacks. How serious is it? Russian military doctrine views an attack against its IoT SCADA infrastructure as a deployment of a weapon of mass destruction, and it therefore reserves the right to retaliate in kind. What does that mean? It means if you turn off the power in Moscow, they're going to export to you a bucket load of sunshine in the form of an intercontinental ballistic missile. The problem is we've become so dependent on these systems for our daily lives, right? Petrol pumps, power, water, sewerage. These systems are critical to our daily lives, and you start taking out water distribution and people start dying very, very quickly. When you look at it, it's amazing how much we've become dependent on these technologies. It's also amazing how much these technologies weren't designed with security in mind. If you go back to SCADA, SCADA originally ran over an RS-232 port, and I'm old enough I can remember what that is. Very big cables running around all over the place, wasn't designed to be connected to the internet, was designed to run things like, dams, water distribution, power, nuclear reactors and things like that. The problem is, just-in-time technology now says, well, we can optimize these things, we can connect them to the internet, we can have things delivered just in time, which is great, except it brings with it a level of vulnerability. Now, when you're doing forensics in the real world, like I do, certainly in the UK, you're governed by what's called the Police and Criminal Evidence Act. And the Police and Criminal Evidence Act defines basically what we mean by the term forensics, because it has a particular meaning in a legal framework, and what you do in terms of storing forensics, processing forensics, incident management, and things like that. So it says the moment we have a forensic artifact, a legal framework kicks into play, and that is that forensic artifact must be accounted for from then on. You must be able to show a chain of custody from the point the data was seized all the way through into a criminal proceedings. Most courts work on the rule, in fact, all jurisdictions work on the rule called the fruit of the poison tree. What does that mean? It means that if you corrupt any piece of evidence, anything that flows from that evidence is viewed to be poison and therefore inadmissible in a court of law. This is why things like chain of custody are so important. To help us with forensics, because originally forensics was a bit of a hit and miss episode, we have a set of standards, ISO standards. And basically, they cover things like, for those of us that do forensics, 17025, which talks about calibration of a forensic lab and how you do forensics, guidelines for incident response in terms of how do you respond to an incident, how do you collect evidence, how do you store evidence, how do you process evidence, how do you write a report, how do you do your analysis, how do you make these things reproducible. When I used to teach forensics, I used to say to all my students, first and foremost, you are a scientist. What protects you is reproducibility. And that reproducibility is built on a basic understanding of how things work and how things behave. So that when you're imaging a hard drive, you know what you're doing and you know how the hard drive behaves and you know how the file system behaves. And I haven't tampered with the hard drive. So if I give you the hard drive and you repeat my experiment, in principle, you should get the same results. It's all about what we call the Socratic method, that is reproducibility of results, in order to be admissible in a court of law. Oops, sorry, where are we? There we go. Right, so how do we do forensics? Well, old-fashioned forensics, as we call it, as it were, relates to things like hard drives, solid-state drives, USBs, phones, smartphones, and things like that. And what that says is, I grab it, I image it, I analyze it, and I write a report. So I have a documented process. My documented process says, this is how I get a hard drive. This is how I take it out of the computer. These are the evidence bags that I use. This is how I image it. Now, forensics has a golden rule, which is do no wrong. That is to say, don't tamper with the data, don't damage the data. Any action you do on the data should not damage or interfere with that data in any way. That's why here you'll see I'm using a write blocker. What a write blocker does is it stops write requests going from my computer to a hard drive. Because the moment you plug your computer into the hard drive, your computer starts talking to it and starts writing data to it. So a write blocker allows me to stop all of those write requests and only do a read. And that will give me a forensically sound image. So I can remove the hard drive, plug it in. I can do the same for the phone. I take the phone, I plug it in, smart tablet, etc. I then use forensic software to forensically image it. That allows me to produce a set of MD5 hashes, which can be used to validate the device. So if I have the hard drive and I image it, you have the hard drive and you image it, you should get exactly the same set of hashes. If you don't, something's changed. I can then analyze it and produce a set of results. Now, in the forensic world, we have a really good set of tools out there for analyzing disks and mobile phones. And some of them you might have heard of. People like Encase, Access Data, Magnet are typically what we use for analyzing hard drives. Paraben, Cellbrite, Oxygen are typically what we use for analyzing mobile phones. Although some devices, some things like Encase and Magnet now do both. Doesn't really matter. The point is, we have a really good set of tools, a really rich ecosystem out there allowing us to do forensics. And I can take these tools, Encase, Access Data, I can analyze them, I can use them to produce a report, and I can then submit that report in a court of law. And that's going to be accepted, right? These are standard tools. We're not going to challenge the tools. And forensic labs use a lot of these tools, right? I mean, you know, the process is well defined. We get it, we image it, we analyze it, we use a standard commercial tool, commercial license, right? The tool's been developed properly and testing and things like that. And if the tool is challenged in a court of law, these companies, Encase, Access Data, etc., will defend their tools in a court of law. So I don't have to worry about it. Well, then suddenly IoT burst onto the system, into the world, as it were. And the problem we have with IoT is that we don't have any forensic tools for IoT at the moment. How you do forensics on an IoT environment is very different from how you do forensics on standard environments. See, if I'm doing forensics on a phone, I grab the phone, I have the phone. If I do forensics on a hard drive, I grab the hard drive, right? I take it away to my lab. Right, I analyze it, I sprinkle my analyzing dust over it, I image it, and it creates a report for me. However, when you're talking about IoT, that's not always possible. And the reason why it's not always possible is because A, you may not know where the device is. Now that might sound really odd, but it's actually very important. So if I'm a power distribution grid, I've worked with power companies where you've said to them, where's this SCADA processing node? And they said, oh, we know where that is. You go, great, where? It's in a field. Yeah, which field? Oh, it's called 20-acre field. Great. Do you know where exactly it is in that field? No, it's buried underground. Great. So what you're telling me is you know it's somewhere in a 20-acre area. Yep, that's pretty much it. That's what we're telling you. So A, it's not always possible to know where these things are because they are geographically distributed. Also, it's not always easy to access them. You know, some of these IoT devices are placed in nuclear reactors, and I don't really fancy going into the heart of a nuclear reactor with a screwdriver in order to retrieve a device. You know, not unless you fancy growing a third limb. So you often can't remove the devices. You might not necessarily know where the device is. Also, how do you forensically remove data from an IoT device? Sounds simple, but it's actually quite difficult. Normal forensics says, I turn the computer off, I take the hard drive out, the computer's turned off, I imaged it. With IoT, I might not be able to do that. If I've got an IoT device controlling a nuclear reactor, unplugging it might have bad things happen. I don't want to happen, right? You know, the same with industrial process control systems for chemical plants, right? You know, unplugging a flow valve in a critical reaction can cause it to go bang. If you're not careful, you end up with something that looks like Bhopal. So it's not always easy to switch these things off. So I might have to access them in situ. Well, can I access them in situ? How do I get the data off? Geographical areas could be huge. I'm dealing with volatile data. Now, it's an important thing with volatile data because everything I've talked about so far in forensics has been the hard drive is turned off, the phone is turned off. You can image these things, right? And in principle, you should get the same result. The problem that you have with volatile data says the data is changing underneath you all the time. So if I take a volatile device and I image it and I leave it for 10 minutes and I image it again, those images won't necessarily be the same. So how do I know if they've been tampered with? Well, what it comes down to here is the policies and procedures that you use. And again, have they been tested? The other problem we have with IoT is non-standard forensic formats. Yes, we're starting to move into a world where we're talking about them running operating systems like embedded Linux and embedded Windows, and that's really helpful in the forensic world. But actually, there are a lot of devices out there running embedded applications that aren't designed as an operating system, right, and loaded straight into memory and execute on ARM core processors. So we have non-standard data formats. We have a lack of security within IoT devices. A lot of IoT devices, in fact, I would argue just about all IoT devices, are not designed with security in mind at all. Right? They're designed to deliver a specific service. Take your car, your sat-nav system, right? Wasn't designed with security in mind. It was designed to deliver a sat-nav service. Your car engine management system wasn't designed with security in mind. And yet increasingly, as cars are coming online, car companies are suddenly finding that they're having to retrofit security to a lot of their products because they were never designed with security in mind. And arguably the biggest problem we have is the lack of forensic tools. As I discussed earlier, there's a lot of mature forensic tools out there in the areas of hard drive forensics, where we can talk about access data, power burn, people like that. And in the IoT world, you're very much down to hardware debugging tools, you know, hex editors and things like that. None of these tools are forensics tools. None of these tools were designed with forensics in mind. So how do you do forensics on an IoT device? Well, the first thing you have to do is prepare, right? And you have to understand the nature of the hardware devices that you're dealing with. Excuse me a moment. So you have to understand your architecture. And the problem you have here is many IoT systems can be 50, 60 years old, running on 6502 processors, right? You know, and people say, well, why is that the case? Well, it's the case because these manufacturing plants were built 50, 60 years ago. They still run, they still operate. They do what they're meant to do. There is no need to change them. There's no need to change the technology. So understanding your technology, understanding your system requirements, and therefore understanding possible attack vectors is critical in understanding your forensic processes. Typically today, we talk about ARM core. Most IoT devices that you see, whether it's your phone, your car, etc., are going to be running on an ARM core processor. But there are other processors out there. And if you go back into the world of SCADA, you can very easily be talking about Motorola M68000 processors or even 6502 processors. You know, we're going back to the days of the Sinclair Spectrum, the BBC Model B. That's when a lot of this technology was actually used in and is still being used. Second thing to do, is to determine the types of attack that you're dealing with. Do you have a physical air-gapped system? If you do, you're talking about an insider threat and you can deploy security measures appropriately. If you're talking about a system that is connected to the internet, then you have certain attack vectors. You know, if you're talking about centrifuges for nuclear reactors, you're talking about, as we saw with Stuxnet, infection via USB. So understanding how you can be attacked can help you develop and deploy mitigations and control in that area. The other thing is that when you have been attacked, you need to isolate those infected areas. And that's not as easy as it sounds because it can mean shutting down a manufacturing process. If you take most production lines at the moment, right? I live in South Wales. We have the Aston Martin production facility just down the road. It's robotic. It only employs about 20 or 30 people. And that's not to build the cars, that's to service the robots. If those robots get hacked and you have to shut down a production line, that's a whole production line you've taken down. Think about it in terms of producing water. If I have to shut a dam down and we're not pumping water, that affects people, or turn the grid off. Or what about sewerage? What about a chemical manufacturing plant? These have business implications, and so it's not a pure technical decision as to what's going to happen. Assume I can isolate the infected areas and I can gain access. Big assumption, but we'll work on it. I then need to prioritize my data sources that I'm dealing with. Some data is held in memory, so I might not be able to turn the device off. I may want to image it and stitch it. Some of them may be writing to SD cards, USB flash, or things like that, in which case I can remove those potentially and look at them later. I can perform data acquisition, I can analyze my data, and I can then create a report and create a set of recommendations. And this is what we call the IoT forensic incident model, right? But it's all about preparation. It's not about picking up the phone at 5 o'clock on a Sunday evening and saying to a forensic expert like me, Andrew, I've been hacked. Help! What do I do? What do I need to send you? In IoT, it's all about preparation, understanding your architecture, understanding. So given that we want to access these things, how can we access them? Well, we're talking about accessing them at the electrical level. If you're lucky and it's running an operating system such as embedded Unix, so perhaps it's running something like BusyBox or something like that, most people here will actually have an embedded device in their home that they might not realize it. It's called an ADSL home router. Your ADSL home router is actually an IoT device running embedded Linux. And if you open it up and look inside, you'll probably see a UART connector. And a UART connector will basically let you connect to it. And you can have a text session on there, right? And, you know, those of us that are old and cynical like me, right, can remember when we had VT100 terminals, and all you young, funky people and in your 30s won't know what a command line is, right? Because I'm showing my age. But UART was the standard way that you have a command line, and you can type in commands on Unix like ls, pwd, and things like that. And you can talk to it. If it's a Unix box, I can start using Unix tools. I know how to do that. But a lot of devices aren't. A lot of devices are running hardware-specific applications, either via what we call an ASIC, an application-specific integrated circuit, or FPGA, field programmable gate arrays. and they load software that they execute at the time they're switched on. And the standard way they do that is via an interface called SPI, Serial Peripheral Interface. And that uses 4 signals to basically load data into a CPU. Now, the good thing about SPI is that SPI sits on a flash, and we can access and image that flash, so we can take a copy of the application that's running, we can reverse engineer it, right, and we can understand what's going on. The downside about it is that that SPI flash is not protected, in that anyone who has physical access can access it, and if you have access via the operating system, you can access it. So SPI flash can be modified, but that's great from a forensic point of view because that's what I'm looking for. So we can use tools like SPI flash to allow us to read it off and write back to it. The other thing we have is JTAG. Now, JTAG comes about as integrated circuits have got smaller and smaller and smaller, so our need to test integrated circuits has got harder and harder. And so when we originally did integrated circuits, we used to have what was called a bed of nails. And this was a series of pins that came down onto an integrated circuit, and you could use to test an integrated circuit. As circuits got smaller and smaller, that wasn't possible. So a standard was created called JTAG, the Joint Test Action Group. And they came up with a standard, a software standard for basically testing devices. And this software standard was originally done to allow us to test and see if an integrated circuit was working. If it was, great. It's grown since then, and it's now used as the standard on-chip debugging software. You see, we're all used to writing programs. And when you write programs, right, and you debug your programs, you debug them in one of 2 ways. You either use a debugger like GDB, or you use a print statement that prints out something like, I'm here, I'm there, oh my God, I shouldn't be here, I definitely couldn't be here, something's gone catastrophically wrong and I need to figure out what it is. But we use debuggers, right? We debug our software, we run our software, we simulate our software. Well, the same is true when I'm developing a hardware application. I need to be able to debug it. And so we have on-chip debuggers that make use of JTAG to allow us to debug the hardware. Now, these on-chip debuggers are great because what they will let us do is they will let us stop the CPU and they will let us access all the devices on the JTAG chain, and that includes the memory, which means I can dump out the memory of the device and I can actually start looking and seeing what that device is doing. The hard bit with all of these, SPI, JTAG, and things like that, is that on early IoT hardware, they were very easily identified. IoT hardware developers have realized that from an IP protection point of view, they want to protect where these things are. So they've made the pins much harder to detect in modern IoT devices and modern embedded systems, right? You have to go probing around on a PCB to figure out where they are. And this is why preparation is important, because when I'm doing forensics on an IoT device, I need to know what that IoT device is so I can prepare to understand the PCB, how the board working, and where the test points are. The other thing you can do if everything fails is what we call a chip off. This is where you get a heat gun, you melt the solder, you remove the chip, such as you can see here, and you bring the chip into a reader and you read it, right? So I can use a reader like Xilex, Dataman, etc., in order to read the chip, dump the contents of the chip out, and analyze them. The important thing to notice about chip offs is all the testing I've talked about so far, SPI, JTAG, UART, etc. It's invasive, but it's non-destructive. I'm not destroying the device. Yes, I may need to power cycle the device to bring it back up, but I'm not destroying the device. A chip off is a destructive attack, right? Once you've removed that chip, getting a chip back on a PCB can be very, very difficult. So chip offs is always the last avenue that we use in the forensic world because it's a destructive test. And the problem we have is I started off at the beginning by saying one of the rules of forensics is thou shalt do no harm. right? Yet chip off violates that fundamental rule of doing harm, because what am I doing? I am destroying a piece of evidence, right? I am taking my PCB, I'm removing the chip off it in order to read the chip, but I am destroying the embedded system, okay? And so that needs to be very, very carefully documented. So the key thing about all of these that we need to be mindful of when doing IoT forensics is that preparation is everything. When we talk about forensics of hard drives, right, so you come in one day and somebody's done something naughty, there's a pornographic image on a computer, right, you can bring in a forensic team, they can analyze the computer. They can only do that because they've been trained to analyze hard drive. They know what a hard drive is. They know how a hard drive behaves. They have policies and procedures to deal with taking the hard drive and imaging it. When we're talking about IoT, we're talking about a vast array of devices. See, when we talk about hard drives, we're talking about the communication standard that hard drives use. And there's only really two, SAS and SATA are the interfaces, and that's SCSI or ATA. So I've only got two interfaces, I've only got two languages to deal with. When we're talking about embedded systems, you can be talking about, custom hardware, custom protocols, etc., etc. Take, for example, a good example is the video world. When we do video on CCTV, one of the problems we have is the encoding mechanisms used to encode it are vast and varied and wonderful. And because you're all talking about compressing that data down onto a hard drive, you could be talking about custom compression algorithms. So video forensics is very difficult because you're trying to figure out what protocols have been used. The same is true of IoT. You're trying to figure out what the devices are. That's why the process model is so important. Understanding your hardware, preparing for an incident, rehearsing for an incident, working with people so they understand the hardware. Or to put it in the words of Benjamin Franklin, by failing to prepare, you are preparing to fail. And there I will pause, stop, say, hopefully I've lined up my ducks. Hopefully you found